There we go. Hi, guys. Okay, so we are in your notes on page number 4. You are also going to want to have your reference tables reasonably handy. We're going to be talking about a new reference table. Okay, we're going to be talking about a new reference table today, which is going to be table F, which is on page 2. So I would recommend maybe having that out as well. All right. Our video for today deals with double replacement reactions. So a double replacement reaction, you are going to have two compounds reacting to form two new compounds, okay? Double replacement reactions also sometimes are referred to as double displacement reactions. Just like single replacement is sometimes single displacement. It honestly just depends on what textbook you're reading and what your professor calls them. So they mean the same thing. But when you're looking at a reaction and you're trying to figure out what kind of reaction it is, the first thing you always do is you look to see how many reactants are there and how many products are there. We know, based on notes that we've taken previously, that if you have, showing my notes here, two things turning into one thing, it is a synthesis reaction. If you have one thing breaking apart into two, it's a decomposition. We said when we did single replacement that you have two reactants, two products, but your reactants would be an element plus a compound, and your product would be an element plus a compound. With double replacement, you're doing two compounds becoming two different compounds. So what happens is that you have an exchange of ions between the two compounds. In other words, swap the cations, so the positive ions, are typically the metals. So this is often going to be between two ionic compounds in aqueous solution. So you have two aqueous solutions, you combine them, you swap the cations, and you make something new. So as we look at this first example here, we have H2SO4, which is sulfuric acid, plus NaOH, sodium hydroxide. Think about H2SO4. The cation, the positive part, is the hydrogen, the H plus ion. In the sodium hydroxide, it's the Na plus. It's always, when you're looking at the compound, it's the first thing, though that's what you swap, the first elements. So this is what's going to trade places. Now, anytime you make a new compound, you always have to think about charges. So when I do this swap, I'm going to have Na, which has a +1 charge, and that's combining with SO4, and SO4 has a -2 charge. So think about what the formula would be for this compound. It would be Na2SO4 when you cross and drop. So that's the first thing. The other compound then, we have hydrogen. Now, when you do this swapping, the little subscript, the 2 on the hydrogen, disappears. You do not swap subscripts. The only exemption to that is if the subscript is part of a polyatomic ion. So like the 4 in the SO4, that's part of what makes it a sulfate ion. So you keep the 4 on the oxygen in the SO4. But the 2 on the hydrogen here, we get rid of. So hydrogen has a +1 charge, and we're swapping that with, all right, so then it's with hydroxide, which is a polyatomic ion. So put some parentheses around this, at least for the moment. And hydroxide, OH, gets a -1 charge according to table E. So think about crossing and dropping. What do you make? HOH. Now, what is HOH? It's water. So you can write water as HOH, or you can write it as H2O. Both are perfectly acceptable. The reality is that a water molecule can break apart into hydrogen ion and hydroxide ion, so it's not wrong to think of it as being HOH. We're just more used to seeing water written as H2O. So we have that swapping. Now, as we look at the next one, we have FeS. Fe iron is going to be our cation in this. We're combining it with HCl, hydrogen being the cation in the HCl. So when I do my initial swap, again, think about these two things trading places. I will form, let's see, H is with S, and let me look up charges real quick. Hydrogen is a +1 charge. Sulfide is a -2 charge, according to the periodic table. So when I cross and drop this, I wind up with H2S. Okay, so that's that. And then we also create, let's see, Fe, and that's with Cl. So let's think about charges here. So the charge on the Fe, when you look at Fe on the periodic table, what you see is that iron can be either a +2 or a +3. So which iron am I using? Well, you have to figure out which iron was in the original compound. I know the sulfur was -2. So to balance that out in this original compound over here, FeS, this iron had to be +2. So there you go, +2. The chlorine then, when I look at chlorine, chlorine is a halogen. It's a group 17 element. So its oxidation or charge, I should say, is -1. So cross and drop there. We wind up with FeCl. Okay, that got funky. That should not be weird. Formatting got real weird through here. There we go. Okay. Looks like that. All right. So our products are what we have going on. Move my head here. That's my answer. That's my answer. Now I could take this a step further and say, all right, now that you know what your products are, balance it. So to do that, going back to this initial problem, I would need to put a 2 in front of the NaOH, and then I would need to put a 2 in front of the HOH. Down in this one, I need to put a 2 in front of the HCl on the reactant side, and we're good to go. So look at this next one. We have AgNO3 plus NaCl. Again, think about swapping. So what do we make? We make Na, which gets a +1 charge, and NO3, which is a polyatomic ion, which gets a -1 charge. And then those are combining. Here we go. The other way, we have Ag, which gets a +1, and Cl, which gets a -1. So what did we make? We have NaNO3, because I don't have to add any subscripts to that thing, and AgCl, which I don't need to add any subscripts because it's +1, -1. Okay, so there you have it. And those are my answers. I would recommend doing the steps exactly as I've been doing them, okay? When you do your initial swap, write down the ions with the charges, then cross and drop, then write your actual products, then balance, okay? Now here's the thing though, guys. Just because you mix two things together doesn't mean there is always going to be a reaction. So in order for a double replacement reaction to occur, one of the following things has to happen. One of your products needs to be a molecular compound. Molecular meaning made of all nonmetals, right? Such as water. So if you see a double replacement reaction where one of your products is water, which can also be written as HOH, that is a clue that the reaction will actually happen. This happens when you mix together acids, so things that start with hydrogen, with bases, things that end with OHs. So on tables K and L of our reference table, here and here, there we go. You have common acids, common bases. If you were to mix any of those together, you're going to make water, okay? That's one scenario that will force the reaction to happen. The next thing is if you notice that one of your products is a gas. So like in this example here, if I were to ask you, why does this reaction happen? If that's not what I wanted. You can say this reaction happens because I make a gas, okay? And then lastly, if one of your products is a precipitate is a solid. So if you are looking at a reaction and you see, oh, look, I make a solid, that is a clue that the reaction will actually happen, okay? And that's what we're going to spend the rest of this video on, is talking about how do you know if you make a solid. This is an important point. I'm going to just highlight it here. if you do your swapping and then you realize that both products are aqueous, it means the reaction doesn't happen. Okay, so you actually have to, unlike with single replacement where you can look on table J and immediately see whether reactions happen or not, with double replacement, you actually have to do the swap. And then you have to figure out, did I make a precipitate a solid? If not, if you only made stuff that's aqueous, there's no reaction. So let's get some practice problems with this. I want to take a moment. All right, so let's take a look at this one. We have sodium sulfate and barium chloride. So to speed this up, I'm going to tell you sodium sulfate would be Na2SO4, okay? And we're combining that with barium chloride, which is BaCl2, right? So think about what is going to happen here. We are going to swap the sodium and the barium, okay? So when I do this, I would have Ba, which when I look up its charge, it's a +2, and SO4. When I look up its charge, it's a -2. So do I need to add any subscripts to this? No, because they cancel out. So this would be BaSO4. Okay. The other thing that I create then would be Na. You'll notice when I'm doing this swapping, I'm not carrying over that little 2 subscript off the Na. So just Na+1 and Cl -1. Again, I don't carry the little 2 subscript over here. Cross and drop. Think about what's going to happen. Do I need to add any subscripts? No, because it's the +1 and the -1. So this is going to form NaCl. Okay. So as formulas, this is what we have going on. Copy. I'm just going to rewrite it. Copy. So in words, if we were talking about the word equation here, and I'm just going to plop this up at the top, when you are given word equations, if they ask you what is created, all you do is you swap the first words. So I am creating barium sulfate and sodium chloride, okay, which is what we have down here. So then to ask yourself the question, well, does this happen? So let's talk about Table F. Table F is entitled Solubility Guidelines for Aqueous Solutions. And here's what we have. We have basically 2 separate tables here, okay? The table on the left, we're going to focus on this one first. You can see it says ions that form soluble compounds. Soluble means they do dissolve. So if you have one of these things, we would mark it as aqueous, meaning it does dissolve. So for example, if you have any compound that has a group 1 ion in it, like sodium, it is automatically aqueous. There are no exceptions to that. So heading back here, NaCl, we just said Na is a group 1 ion. Group 1's ions are always soluble, no exceptions, ergo NaCl is AQ. You'll notice though some of these have exceptions to it. So when we look at the other product, BaSO4, here's SO4, sulfate. Typically, sulfate ions are soluble, meaning they do dissolve. They would be marked as aqueous, except when those sulfate ions are combined with silver, calcium, strontium, barium, or lead. So if you fulfill one of these exceptions, you do not dissolve. You would be a precipitate, which means you're a solid. So I would mark it as an S. So BaSO4 gets marked as an S. Why? Because sulfates, when combined with barium, do not dissolve. So it's a solid. So does this reaction happen? Yeah, it does. How do I know? I made a solid. All right, so lead 2 nitrate and sodium iodide. Let's think about what would happen here. We're going to swap the cations, so the sodium and the lead 2. Just going to scoot my face back over here for a minute. So what am I making? I am making sodium nitrate and lead 2 iodide. Okay, so as formulas, lead 2 nitrate is going to be Pb, that's lead, NO3, 2. How do I know that? Because lead is Pb, The Roman numeral tells me it's a +2. Nitrate is a polyatomic ion. It is NO3, and nitrate has a -1. Excuse me. Okay. So then that is combining with sodium iodide, which is NaI. I know that because sodium is an alkali metal. It's a group 1 metal, so it's Na+1. And iodide is iodine -1. It's a halogen. Okay, so then when I do my swapping, we have NaNO3. Na is a +1, NO3 is a -1, so don't get any subscripts. And we have PbI2. All right, so what do we got going on here? NaNO3, let's go to table F and see. Will this dissolve? Well, we already said Na, always soluble, no exceptions. Ergo, NaNO3, definitely aqueous. And you only have to find one of the ions. You only have to find the cation. You only have to find the anion on this table. You don't need to find both pieces. Now let's look at PbI2. Well, here's iodine. It's a halide. Halides are typically aqueous. They do dissolve. They are soluble in water, except when combined with silver, lead, or mercury. So PbI2 is going to be insoluble. It would be marked as a solid. So does this reaction actually take place? Yes. Yes, it does. Why? I form a precipitate. I made a solid. Okay. So just to get some terms in here, soluble means it does dissolve in water. Insoluble means it does not dissolve well in water. Now, when we say something is insoluble, to say it doesn't dissolve at all would not be true. Because to a certain extent, everything will dissolve given enough time. Like when you talk about a rock, you wouldn't look at a rock and go, oh yeah, that rock dissolves. It's a rock, right? You throw it in the water, it's still going to be there the next day. But if you take that rock and you put it in a river for 1,000,000 years, is the rock eventually going to dissolve? Yeah, it is. So nothing is really completely insoluble per se. And of course, there's exceptions to everything. But typically speaking, when we refer to something as insoluble, it just means it does not dissolve well. It's not going to dissolve well enough that in the course of a normal experiment, you would be able to dissolve it. So insoluble, another word for something that is insoluble is to refer to it as a precipitate, and a precipitate is another word for solid, okay? So take a look at this chart just to get some additional practice here. So NaF, soluble or insoluble? Well, let's think about it. What do I see? I see Na. Na is a group 1 metal. What does that mean? It's soluble. Are there any exceptions? No. So this would be soluble. We would mark it as AQ. If I head down to the next one, we have MgSO4. So I'm going to go here and look for either of those pieces, Mg or SO4. Well, here's SO4. SO4 is typically soluble. Mg is not an exception to that. So this MgSO4 is soluble. And I would mark it as AQ. So the SO4 is what gave it away here. The next one down, we have CaNO3 So as I look here, here's NO3, nitrate. Nitrate is always soluble, no exceptions. So this would also be soluble. I'd mark it as an AQ. PbI2, we literally just did this one, right? So here's iodine, usually soluble, except when with Pb. So this would be insoluble, which means we'd mark it as a solid with an S. And then SNS. So now we're on this other side of the table here, which is kind of the opposite, where they give us ions that form insoluble compounds, which means they do not dissolve. We mark them with an S. And then the exceptions to these would be soluble. They do dissolve. We'd mark them with an AQ. Okay? So SNS. I don't see SN anywhere. I don't see tin in either the soluble column or the insoluble column, but I do see S, sulfide, over here. Sulfide is typically insoluble, except when it's with a group 1 ion or ammonium. Well, tin is not a group 1 ion. It's not ammonium. So what that tells me is that SNS, I just keep moving my head, is insoluble. I would mark it with a solid, okay? So here's what I'm gonna ask you guys to do. I'm gonna pause the video, check out these last 5, restart the video, check your answers, and then that'll be it. So let me know what questions you have, okay? I'll see you in a minute. Bye. All right, guys, so here they are, NH4 2CO3. Anything with NH4 is always soluble, no exceptions. Here it is, ammonium, soluble, no exceptions. So soluble. Ag2SO4, well, SO4 down here, typically is soluble, except when it's with Ag, so that made it a solid. LiOH, well, we know lithium is a group 1 ion. It's always soluble, no exceptions. Even if you were looking over on this other side of the table with the hydroxide, you say, but Mrs. Saul, hydroxide is insoluble, so what's going on? Yes, hydroxide is insoluble, except when it's with group 1 ion. So the fact that I paired that hydroxide with lithium made it soluble. So then our next one, we have BaOH2, which is soluble. Why? Well, OH is over here. It's typically insoluble, except when that OH is with Ba, barium. So barium hydroxide is going to be soluble, AQ. And then Na2CrO4, Na group 1 ion, always soluble, no exceptions. Even if you're looking at the chromate over here, CrO4 is usually insoluble, except when it's with a group 1 ion, okay? We'll get more practice with this in class, ladies and gentlemen. Let me know what questions you have. Sorry this video ran a little bit long. We had a lot to get through in this one. And I'll see you soon, okay? Bye.